So I have this lecture on process placement, which was quite a new one I wrote for the MSc last year. So, okay, motivation here, which you've spotted, is that MPI talks about processes, each with their own unique rank, but HPC systems have a structure. Many physical CPU cores on many different nodes. CPU cores on the same node communicate via shared memory. Communication between nodes uses the network. Inter-node communication is slower than intra-node, especially in terms of latency. So the question, the first one is, you're talking about optimizing the mapping of processes to nodes. But the first one is to how are they mapped? You know, how can we control this? It's system dependent, but okay, obviously on desktop computing, you run many more processes than cores, and they're always shuffled around. Of course, that's not true on parallel computing. Here, parallel computing, we match the number of processes to the number of physical cores. That was just an aside. So we match the number of MPI across the physical cores, right? We have to make sure. So this is about process placement in its generality. So the first thing is that you make sure they do not migrate between cores. You make sure they're pinned. So, but that is done automatically by the MPI library, at least on a system like ARCHER2, and you have to worry about hyperthreads. That's not what you were asking about, though. Okay. Typically, if you're running 256 MPI processes on 4 nodes, and each node has 64 CPU cores, almost all systems will map them linearly, 0 to 63 on node 0. So I think, although the trick is mapping to different nodes to optimize the inter-node communication is difficult, but what you should try and do is try and minimize the inter-node communication. Let's hope that the batch system has given us a lot of nodes which are physically close to each other and therefore physically close on the network, a minimum number of hops between them. How do we optimize so that at least we use the network as little as possible? And almost all systems put ranks 0 to 63 on node 0, do a linear mapping, you know, of to nodes. That may not be optimal because if we have a 64 by 1024 array and we have 250 MPI processes, we might choose to say, okay, we will do a 4 by 64 distribution so that each local domain is 60 by 16. So what I've done here is I've got a 4 by 64 array of this is 256 MPI processes. If you think about each process communicates with 4 neighbors, and so 120 messages are sent over. So each process here communicates with 4 neighbors, but these are the divisions between. So this solid line represents the nodes, and this is bad because if we look at our domain, it's split up long and thin between nodes. So a lot of the messages are going over the network, and the communication between 62 and 126 is going over the network. That's going over the network, and so 128 messages are sent over the network from each node because we have a non-optimal mapping of processes to nodes. So that this is a slightly contrived, well, not necessarily a contrived example, but what I've tried to draw here is the mapping of these solid blocks of the nodes, each which have 64 processes and ranks 0 to 63 on node 0, 64 to 127 on node 1, and so on. And with this distribution, the distribution of the physical domain to nodes is long and thin, which is bad. It means we get lots of messages. We get a very high surface area to volume ratio. It'd be much better to switch the axes. And now, okay, if we do it like this, only 8 messages per node of the network, okay? How do we do that? Well, there's 2 ways of doing it. One is we could use the Cartesian topology and try and let MPI reorder them itself, but that may not work. Or you can do the remapping by hand. An MPI cart split is a routine which allows you to do a completely general permutation of ranks completely general remapping of ranks. So that might be the way to do it. Tools are nice actually here. So job launcher options. It's sometimes easier to do the remapping at launch time. So what I'm saying here is you can launch your program and within your MPI program try and optimize the decomposition. But actually, it's sometimes easier to to change the remapping at launch time, to tell MPI don't put ranks 0 to 63 on node 0, put ranks 0, 1, 2, 3. Well, this is a logical remapping, sorry. So it's harder to do, but sorry. Don't put ranks 0 to 63 on 3 on node 0. Put 0, 1, 2, 3 to 8, and these guys, 64, 65, 66 on node 0, okay? And put this block on node 0, the next block on node 1, the next block on node 2. And you can do that because most batch systems will have some complicated commands to let you do this. You can explicitly say, give it a file which says the mapping of each rank to each node. Also, tools can help here. Cray-perf tools will measure the communication in your program and then suggest to you, actually give you a file which says, I think that this mapping of processes to node. So actually, so to get back to your start, Michael, are you running on ARCHER2? I mean, that was my main question, or you think it is a general? Yeah, okay. So you can run using Cray-perf tools. It will spit out, you can get it to spit out a file which actually is a mapping of processes to physical processors. And then you can rerun your program with this special option. I can't remember what it's called, --map or something. You don't have to change your code at all. It just optimize, and that might go faster. It might not, but if it goes faster, it's completely for free because you've always changed. So that would be my suggestion. Would be inject. You can run it through perf tools, get perf tools to spit out a mapping file, and use that at runtime. Does that make sense, Mike? And that's for free. You don't need to change your code at all. So yeah. So that I've not done that for a while, and I'll maybe look up at the break how try and remember how you do it, but that is possible. I've got a slide which maybe answers Michael's question to a small extent. This is a diagram of the network. So groups of processes are heavily interconnected with an all-to-all network. But a group is, I can't remember, a few hundred, maybe 1,000 CPU cores. I'm not sure, but it's that kind of, but that's a physical backplane. That's a piece of hardware on the back of, but then you need to go to physical cables, and these are, these groups are then joined in at a higher level all-to-all network. Well, if you can afford it, you can pay for more using optical connections. So these, you have the physical chassis that you put the processing motherboards into has a backplane which has I'm not a hardware person, but has like this copper interconnect. So there's an interconnect very tightly coupled within a chassis, I think it's Cray call it. But at the higher level, you hope that hopefully the Slurm scheduler gives you a nice dense group of. The problem is it's very hard. You don't know what you're going to get at runtime. So there's only so much optimization you can do. So my advice would be to optimize to reduce the amount of communications that goes across outside a node, but then just hope that the Slurm scheduler gives you nodes which are tightly connected. It'll be very difficult to configure at runtime to take care of anything more than that. Okay, hello everybody. Again, my usual just paranoid check. The audio is okay. If someone could confirm that, just equally important for the recording, of course. But I'll wait a couple of minutes. Great, thanks, William. So the where are we? So the we're going to now talk about collectives. short lecture, hopefully, and then a practical. Tomorrow, just a heads up, we're going to talk in the morning about MPI+OpenMP, which I know a lot of people want to know about. And a lot of current centrally installed applications support MPI+OpenMP. It's useful to know about the details, even if you're not going to write it yourself. It's useful to know about its capabilities, because a lot of modern programs, packages, things like quantum chemistry packages and such, like engineering packages, will support that as an option. And then I'll talk about the RMA access and MPI, which is related to this. It's basically how to exploit the shared memory nature of an ARCHER2 node using MPI, but without calling out to OpenMP, just purely with an MPI. And then I've got a session at the end. But just, I'm going to talk about collectives just now, so if I just get this lecture up. Just need to. Okay, so I should be able to share that now. So there's a slight delay there. So the issue here is, one of the major optimizations you can do, the simplest optimization. Excuse me, I just need to close the door. Apologies for that. One of the simplest optimizations you can do is to use collectives. But I wrote this lecture because I come across a lot of cases where people didn't think, where it's not obvious how to use a collective for the pattern you want to do. And the classic one, it's a very common one, and it illustrates all the majority of the issues I want to talk about, is gather and scatter. So the MPI gather routine, in fact, why don't I just, before I, maybe worthwhile if I just take a quick, am I going to be, I can't know if I'm using gather or gather, fine, okay, fine. So, so what I will do is I will just briefly recap on what MPI gather is. Just to so often, just to recap, at the end of an application, you want to gather. I'm saying you shouldn't really do this for I/O, but it's a common operation to do for other reasons. Is to gather data. So you have 1, 2, 3, 4, 5 processes who have data A, B, C, D, E. This is shown as being a scalar, but it could be in general, it will be a subsection. It could be an array, length, whatever. And you want to pull that together, say onto rank 0, rank 1, into a single array. And gather takes A, B, C, D, E. A call to gather takes A, B, C, D, E across processes and collects them together, gathers them together onto a root process here, rank 1, in rank order. So, for example, if you had a vector, a very long vector divided up into chunks, standard domain decomposition across processes, you could collect this back together in the correct order using a gather. And this, it's quite a simple prototype. You have a send buffer, a send count, and a send type, which is this data here. A receive buffer, a receive count, and a receive type, which is this data. Sorry, I'm going the wrong way. Which is this data here. And the data is automatically collected onto a particular root process. Here we've said root equals 1, although more often than not it would be root equals 0. So I have my own MPI course, a very simple test program where people do this. And immediately people say, I don't have a vector, I have a 2D decomposed array, decomposed into chunks. And unfortunately, and I'll demonstrate this with the next slide, it does not immediately appear that you can do a gather of a 2D array and get it in the correct order. And that means that then people do it their own thing. What they do is they have each process here send the data one at a time to rank 0, and that becomes the bottleneck. But it is possible to use MPI gather to do more general things, but it's not immediately obvious how you do it. So I'll go back to the original slide. It's disappeared. How can you do that kind of thing? So I'll talk about the motivation, the 2D gather pattern, how we do it. So collectives are a key part of MPI. It's much simpler than implementing your own operations, and much faster than the DIY approach. And there is a flexibility in what processes can take part. So for example, you might say, I want to do a collective, but not across all the processes. I want to do it across a subset of the processes. You might have your processes arranged in the 2D grid, and you want collectives individually across rows of the grid or columns or rows of the grid. You can do that by using subcommunicators. You can create subcommunicators, and then that means that operation is collective, not across all processes across MPI COM1, but across the particular subset. And that is how you could have done that correctly. Done the example I had in the quiz at the start. You would have created two communicators, COM even and COM odd, and done all reducers across them separately. But what if your data layout doesn't match the collectives pattern? What if your data type is not supported? Well, so you might want to do an MPI sum on a data type which isn't supported. You might have your own data type. Now that can be done with user-defined reduction operations, which I'm not going to really cover because it's slightly esoteric. But the real one is the first one. What if your data layout does not match the collectives pattern? The collective pattern for MPI gather assumes a linear array, we can call it a vector, distributed and blockwise across the processes. That is not true for even the simple case of a 2D array distributed across a 2D grid of processes. But you can do it. And it requires quite a lot of setup and a bit of messing around, but it's worth it because your eventual call to MPI gather will be a lot more elegant, but also much, much quicker than what you could write yourself. So my canonical example is a 2D array distributed across a 2D process grid, not a 1D array distributed across a 1D process grid. We want to use MPI gather to collect data onto a single process before maybe performing serial controller I/O to disk. Now I did say that that's not a good use case particularly, but you can generalize it to MPI all-to-all a whole bunch. In fact, MPI all-to-all is probably the one which is most commonly used. But I wanted to use a slightly simpler example. The difficulty here is understanding how derived data types work with collectives. Derived data types are slightly are useful, but slightly hard to work with when you use them with collectives. But if we go through this example in some detail, if you understand this example, it's very straightforward to apply to other cases. So this is my canonical example. I have a 2D grid, which is 4 by 4, distributed across a 2D grid of processes. So each process has a 2 by 2 grid. Now, I've drawn my indices I, J. A lot of people draw their indices I, J as if it was a matrix. I've drawn them I, J. It doesn't. The details don't matter. You could draw it the other way around. The details are slightly different, but the concepts are all the same. So this is a very simple example: a 4 by 4 array, so with 16 elements, distributed across a 2 by 2 grid of processes, and the processes are ranked 0 is 0, 0, rank 1 is 0, 1, rank 2 is at position 1, 0, and rank 3 is position 1, 1. So I assume that I've maybe used a Cartesian communicator to set this up. However, what you'll see is that even in this simple case, rank 3, the red process, does not own elements 13, 14, 15, and 16 as it would have done in a linear decomposition. It owns elements 11, 12, 15, 16. And so if I want to gather this to rank 0, I don't want all the yellow data, then all the blue data, then all the green data, then all the red data. That is what MPI gather would do. I would get 1, 2, 5, 6, 3, 4, 8, 7, 8, 9, 10, 13, 14, 11, 12, 15. It would treat these as just simple. MPI in general doesn't really understand multi-dimensional arrays. It treats things as linear arrays. That's why send buffer is just a linear array, as is a receive buffer. So how do we do this pattern? So does anyone have any, appreciate it's a long day, but does anyone have any ideas? What kind of data types could help us to do it in this? We're not going to receive data into contiguous sections, but with gaps in it. We want to have gaps. So the green data wants to be data, gap. I want to receive into non-contiguous data sections. I do cover this in the introductory course, but I can't remember that. And the trick for doing non-contiguous data sections are things called, for example, vectors. So MPI defines a data type which allows you to have gaps. Now, you could do this by hand. What you could do is you could gather in the default order, yellow, blue, green, then red, and then rearrange the data. Okay, I've seen people do that, but that's really quite ugly. You don't really want to do that. It's a lot of effort. How do I do this with gather? So actually, of course, this red process doesn't really have elements of 11, 12, 15, and 16. What it has is a 2 by 2 local array numbered 1, 2, 3, 4. So this is really, when I say global indices, I'm imagining I have a large 2 by 2, a 4 by 4 array with 16 entries. But of course, when I program that up, what I actually declare on each process is a 2 by 2 array, and I stitch them together globally using my Cartesian communicator. So this is what I want to do here. That's what I want to achieve. So the first thing you might say is, well, okay, this is a vector pattern. Okay, so I should define a vector. So, okay, so I forgot that. So actually, let's forget that these are 2D arrays. What MPI really only understands 1D arrays. So what you actually want to do is this. You've got 4 processes, rank 0, 1, 2, and 3, each of which with an array of length 4, and you want it to be gathered together on rank 0 in this order. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That's what you want to do, and that corresponds directly to this example here, but I've flagged it out and written it as if these were 1D arrays rather than 2D arrays. Remember, in C and Fortran, a 2D array is just a 1D array with a particular indexing convention. That's what I want to do. Now, the prototype for gather is MPI gather send buff, send count, send type, receive buff, receive count, receive type, root, and com. Now you might, if you've seen this routine before, wonder why do I have a different send count and send type from receive count and receive type? Surely if I'm sending from each process 4 integers, I have to receive 4 integers. Well, that generality of having separate send type and receive types is there to allow you to precisely do this pattern, where you send 4 integers but receive 1 vector, and a vector is an object which can have gaps in it. And the reason you're allowed to do that, you might say, how can you send 4 integers and receive 1 vector? Well, the 1 vector contains 4 integers. So the send type and the receive type don't need to be the same, they just need to be compatible. As long as they both contain 4 integers, then you're fine. So you'll actually see a lot of MPI routines have separate send types and receive types. That is a lot of MPI collective routines. And in 99.9% of usage, they're the same, the send type and the receive type, and therefore the send count and the receive count are the same. But here we're going to use that generality that we can have a separate send type and receive type, and also separate send count and receive count to do this nice pattern. So in this case, all processes in COM send count items of type send type from the send buff to rank root. They'll send all this data to the root, which is what we want. And then the root process receives receive count items of type receive type separately from each process, and these are received into receive buff in ranked order. So, but exactly where are they placed? Okay, so the normal MPI gather would do this. Okay, and this is not what we want. Okay, we don't want 1, 2, 3, 4 from yellow, 1, 2, 3, 4 from blue, 1, 2, 3, 4 from red, 1, 2, 3, 4 from green. What we want is to have them split up. But what does it actually do? What it does is the message from rank is received at byte displacement. Okay, rank times receive count times extent of receive type. Okay, so in this case, the data from rank 0 is placed at rank is 0, receive count is 4, and the extent of the receive type is MPI int, and that turns out to be the size of an int, which is probably 4 bytes. Okay, this is a very complicated way of saying they're stuck together in rank order in blocks. However, we need to understand this in its gory detail to do the correct thing with the vectors. But this, for example, the green data, which comes from rank 2, is put at position 2 times 4, which is 8, times size of int, which will be 32 bytes, which puts it in exactly the right place. But formally, the message from rank is received at byte displacement, rank times receive count times extent of receive type. So for basic data types, especially where the receive type equals the send type, okay, this is the extent of the receive type, okay, then this just lines them up in order. However, what happens when you have a more complicated receive? So the first problem is the data pattern on the receive side is incorrect. If I just did a gather, I would get this. And what I want is this. So the obvious thing to do is to set up a vector, an MPI type vector for the receive type. So a receive type is a vector. It is something which has a data, gap, data. So this pattern is the 2 by 2 subsection of my 4 by 4 array. This corresponds exactly to, for example, this data here. It's 11, 12, then we skip 13, 14, then we have 15, 16. All of these 2 by 2 subsections of this big array, or equivalently down here, are vectors of that form. Sorry, I've hit the wrong button here. Apologies for that. Are vectors of this form. However, send count and send type is not equal to receive count and receive type. Let's imagine we've defined that vector. The routine is called MPI type vector. You specify the sizes and the gaps and the displacements and such like. Send count is 4, send type is MPI int, receive count is 1, and receive type is vector 2 by 2, if I call that a vector 2 by 2. But that is legal because they are compatible, as they both contain 4 integers. So that's fine. So that looks fine. I can send the 4 integers, and they'll get split up into this data, gap, data. That looks right. The problem is, I don't just need them to be split up. I need them to be placed at the correct starting position. So I need this to start at the yellow data type start there, the blue one to start there, but then the green one to start there and the red one to start there. So it's already getting a bit complicated. So that's the first problem. The data pattern on the receive side is incorrect, but we can fix that by making the receive type a vector. Problem 1 solved. I'm not going to go into this. Another way of defining these subsections are subarrays, but that's a slight bit of an aside, so I'll not cover that. So this is the required pattern. Okay, I want the first data type to go at 0 times size of int, the second one at 2 times size of int, the third at 8 times size of int, and the fourth at 10 times size of int. That's position 0, 2, 8, and 10. So if you look about it, the second problem is that these displacements are not regular, whereas the standard gather, the displacements are multiples of rank. Okay, they have to go up in multiples of rank, but these don't go up in multiples of rank. They go 0, 2, 8, 10. So that's our second problem. The displacements are not all multiples of each other. So the trick is the displacements received buffer are not regular. If we count in integers, they're 0, 2, 8, and 10. So what we have to do is use a more complicated routine called MPI gather V, which takes vectors of receive counts and displacements. So basically, MPI gather assumes that all the receive counts are the same, 1, 1, 1, 1, 1, and all the displacements are 0, 1, 2, 3. Okay. But what we can do is we can specify these by hand. So it's a more general routine MPI gather V, where you specify now all the receive counts for us will be 1, but we'll play around with the displacements. Okay. But the problem is, remember, the displacement is multiplied by the extent of the receive type, how long the receive type is. Okay. How long is this object? Okay. Well, MPI says this thing is 6 long because the gap between there and there is 6. So although the MPI gather V allows you to place things at different displacements, they all have to be in multiples of 6 integers. And that's not good enough, okay? Because that displacement there is not a multiple of 6 integers. Neither is that one, neither is that one. So it looks like we can't do it because the extent of the receive type is wrong. In fact, we want, if you think about it, we want to offset these vectors by less than their extent. We want the first one to be here and the next one just to be a couple of integers along the way. So the third problem is the displacement and the receive buffer are not multiples of the extent. The required displacement are 0, 2, 8, and 10. Because the extent of a vector 2 by 2 is 6, we can only place them up against each other. So the hacky solution, unfortunately, you have to do it, is to resize the new data type. This problem was noted quite early on in the history of MPI. So they put in this hacky routine where you can tell MPI, look, I know you think this vector is 6 integers long, but let me resize it. I want you to think of it as being a different size. And it's a routine called MPI type create resized. You give it an alt type, which is our vector. You give it a lower bound, which is where it starts from, but we won't exploit that. We always want to start from the origin. You can put in a leading gap as well, but we're not going to do that. So we're not going to use that generality. We're always going to start here. So for us, the lower bound is 0. We give it an extent, and we get back the new type. This extent and the lower bound are in bytes, which is horrible, but they have to be in bytes. And in MPI, you need a special type called MPI ANT or MPI address. You can't store byte displacements in a 32-bit integer. So it's all getting rather complicated, but trust me, it is worth doing because at the end of the day, it allows you to call a single gather call to do the gather. So what we do is we resize the data type. We say we've got the lower bound and our int size. The lower bound is 0. We want to find out how big an int is. We could do size of, but let's use an MPI. With the MPI type get extend MPI int. That just gives you back 4. So what we want to do is we want to resize our vectors 2 by 2 to be the size of an integer. And that's what this does. It says take the vector 2 by 2, resize it so it still starts at the origin, but now has size 4, which was the size of our integer. And we get back something called I've called vec resize, which is the same as the original data type, but is now MPI thinks it as having a smaller extent. And then we commit it. That's just the technicality in MPI. And these are the equivalent in Fortran. Having done all that, we can just then call MPI gather with send buff, send count is 1, and send type is MPI int. But the receive buff is our array. The receive counts are 1, 1, 1, and 1. But the displacements are 0, 2, 8, and 10. And the receive type is vec resize. So if we do that, having done all that messing around, we get the correct distribution. And it's maybe looking at this offline, but that approach will generalize to, if you look at doing an all-to-all, which is like a matrix transpose, you will immediately see that the data types, the send buffers and the receive buffers aren't in the right place. But you can fix that by playing around with data types. So I mean, this looks quite low level and hacky. We have to talk about bytes and things, which is always rather nasty, but it is worth doing because it allows you to use the inbuilt collective routines for more general data patterns. And out of the box, they'll only work for the simplest data pattern, but you can make them work for you if you go to the trouble of studying this stuff. So similar tricks can be used for scatter. And many scientific applications use the all-to-all pattern, as I said. It corresponds to transposing a matrix between row and column decompositions, which is what you do in fast Fourier transforms. There's a vector version called all-to-all V, but it turns out that this has a single, like MPI gather, has a single send type and a single receive type. It turns out that that is often not general enough. So there was all-to-all V for a vector version, so they need an even more general one. They just called all-to-all W. And it allows for multiple send types, multiple receive types, multiple counts, and multiple displacements. And so the standard all-to-all has one send type, one receive type, no counts and no displacements. All-to-all V has one send type, one receive type, but you specify counts and displacements for the received side. All-to-all W has multiple send types, multiple receive types, multiple counts and multiple displacements. There's no obvious counting unit here because all the data types are different sizes, so you don't need to do this resizing stuff. You specify the displacements in terms of bytes, which is horrible, but so I mean, I wouldn't normally give a talk which went into such sort of gory detail, but this is really a barrier that people hit. They learn MPI gather, MPI all-to-all on a course. They learned it with simple vectors. They then go to their own code, the 2D code, and they're scuppered. This allows you to do that. So the technicalities of derived data is going to be complicated. You may have to play tricks with the extents to the collector's work as expected, but it is worth the effort. These are highly optimized. For example, a naive do-it-yourself gather would send P messages on P processes. The optimized collectors would send log2 messages, and that means it'll be 100 times faster on as few as 1,000 processes. 1,000 is 2 to the 10. So whereas your naive implementation would do 1,000 messages, the inbuilt collector would do log2 1,000, which is 10. So these derived data types avoid ugly copy. You could do this with data rearrangement. You have ugly copy in, copy out. In this approach, the rearrangement of data is done automatically by MPI, and these all-to-all V and W are used by many parallel scientific applications. So apologies if that was a bit detailed, but I also promised to go through the results of the halo swapping. I don't know if people got their own results, but I will just do that very briefly now. I ran some results in the interim. You could have run these yourself, obviously. So let's just share that. So what I did was I ran the first one was the defense, was the out. Let's see. Sorry, the Windows terminal is defeating me. No, I want the first one. Apologies for this. I'm having to learn Windows as I go along. There we are. So this was out the box. The default one was each halo contains 1,000 doubles, and I'm doing 10,000 doubles, which is 80 kilobytes, and I'm doing 1,000 repetitions. And I do 1,000 repetitions so that it takes, here. So the send receive did 670 megabytes per second. Now remember, these are way, way down on the data rates that we got for the ping pong. But the reason is this is a real code. And in this code, 128 processes are sending per node. Now remember, all those processes share the same network interface. So, that is why you get a lot less bandwidth than you might get. The ping pong gives you a fake high result, a high watermark. For some reason, the red-black, where you do 2 phases, odd send to even, and then even send to odd, is quite fast at 900. But the send receive, the I send receive, and I receive send, all of which are all these 4 approaches are kind of pairwise. For some reason, the red-black is quite efficient. I don't understand why, but they're all at 670 or 900. But then if I do, also this pairwise one. But as I said in the previous lecture, I think that all non-blocking will be the fastest, and it is quite significantly. over a gigabyte per second, and then the persistent and the neighborhood are all effectively identical. So as long as you can do entirely non-blocking communications, you'll see you get much, much better performance than kind of a naive one, about 50% better than that, which is quite significant. I also upped the data sizes to beyond the eager limit. So I edited the code and reran it. Now 100,000 doubles, which is 800 kilobytes, which I believe was well above the eager limit. And you'll see that, you know, the bandwidth has dropped significantly. And here, all of the pairwise ones are only 500 megabytes a second. Whereas if we do the fully non-blocking, all the pairwise ones are 500 megabytes per second. You do the fully non-blocking, again, it's about 50% faster, 790, almost 800. So there you see, you know, with a simple benchmark verification that setting up lots of non-blocking communications and then telling MPI, look, I've got 12 communications going at once, you sort them all out, is significantly faster than matching them up by hand using send, receive, or any pairwise operation. So that's the only the exercise for today. You're welcome. Sorry, the exercise for this session is based on the collectives. Sorry, that's the lecture, which you didn't want to see. You want to see the exercises, which are down here. So I have a tar file. Okay, so I should actually basically, I'll go back to this here. Remember, I unpacked it, so I'll have the tar file there. So I would expect you to get this from the website, but it's easy for me just to clone the whole repository onto ARCHER2. So we have, here we have collective.tar, unpack it, collective. And sorry, these aren't very consistent, but the first exercise, our MPI gather.c illustrate using vectors for gather operations. These ones illustrate the gathering the 2D arrays as illustrated in the lectures. And there's also some other stuff which does. So if I look at the first one, MPI gather.c, the exercise is just in comments in the top. I want to have data which is distributed like that, and I want to receive it like this. So that's a non-standard ordering. And then that's the exercise. So you need to receive this data into a vector 0, 3, 6, 9. There is a solution there though. Gather sol.c. Again, there's 4 times ones there as well. This is the solution, which involves it prints results from the standard gather, then it prints it does it correctly where you have to do a resized vector. And there's also the 2D version where I've done a matrix version here just to be contrary. I want you to receive that, which is the exact, I've drawn it slightly differently here. It's exactly the exercise I just described in the I don't have any, do I have a make file? Apologies, I don't have a make, so you're going to have to let's grab the Halo Bench make file. Be trivial to, let's do the 4th round one, but you could do it, you could grab a C1 as well. Let's do it. MPI gather 2D.f90. make compile it, and I also want to copy the ARCHER2.job. I'll just run it on one. I think actually this is set up for easiest to do on. I'll just do a really simple example where I'll run on one node and 5 processes, and I'll run on MPI gather 2D. Let's see if it's working. Running. Okay, I must run on 6 processes. So with that, it's hardwired into the code for reasons I just delivered it to be simple. Let's see if it's running. Yeah, it's finished. So if I do a naive gather, I get the wrong answer. It should be 1, 2, 3, 4, 5, 6. It goes 1, 2, 3, 4. Where does it? Oh, it's all over the place. So that is wrong. This should just be a linear number of numbers. But if I then compile the solution, let's call it MPI gather 2D sol. ARCHER2.job, we'll see that if I run the right. So you can't run the MPI program on the front end. So I'll run the solution. Is it running? Yes, it's running. Oh, sorry. Oh, sorry. I called the executable the wrong thing. Sorry for that. It should be running soon. Yeah, there it is. So you'll see that if you do a naive gather, you get the wrong answer. If you do the vector gather, you get exactly the right answer with all the data in the right place lined up correctly. And so if we look at the code, I'll look at the C code, just because I think most of you are C programmers. You'll see that there's a lot of setup here, but it's set up to be nice. You know, it's a 12 by 10, right? The number of rows. Oh, that's why it's split into a 3 by 2 grid, which I just do by hand. There's a lot of simplicity in this program, but it illustrates the example. So the big matrix is 10 by 12. The small matrix is smaller. The local matrix is much smaller. But just to show you, you can look at this offline. The naive gather does this. The local matrix gathers the local matrix into the global matrix, and we see we gather NP by NP integers. That's the number of integers in each process each time, and you'll see you get the wrong answer. But then I have to do the trick where I create a type of vector. I resize it to be the size of an integer, and I commit it. The receive counts are on 1, but I need to compute the starting positions of the received vector. So there's a bit of a jiggery after the displacements I have to place them correctly. But once I've done that, I can do a gather of all the integers from the processes. The receive counts are all 1, but the displacements are non-uniform, and the type is resize vector. And if you see, that does from going from this, which is not what we want, we now get this, which is what we want. Again, it takes a while to get this right, but once you got it right, then it will work forevermore. So I think those are hopefully useful. And the merge sort list illustrates user-defined functions for collectors, but that's really not really as crucial as the data types. So that was really the end of today. Hopefully that made some sense. I've given you solutions there because this is quite a technical thing. So you've got the solutions, you can work out how it goes. I will be around until tomorrow. I am more than happy to answer individual questions, which can be done in chat or through audio or through a breakout session. But as I said, the next lecture is MPI+OpenMP starting again tomorrow. And that should. The only difference tomorrow is that we have a different reserved queue for you'll need to look at that. So to end there, hopefully, even if it's quite a quick run through, if you didn't quite understand the details, you have example codes there which give you examples in C and Fortran on how to do this in practice. I didn't know if there are any questions, but I'll be around till 5 p.m. to answer